Imagine your typical evening at the computer. You are running a demanding video game, streaming a high-definition playlist in the background, and downloading a massive update file. To you, these actions feel perfectly simultaneous. But beneath that experience is a rigid physical reality. Your central processing unit, the physical engine doing the work, is a sequential machine. Despite its incredible speed, a standard CPU core can generally only process one instruction at a time. This creates an immediate mechanical crisis. If your game, your music player, and your browser all tried to access the processor at the exact same moment, the hardware would instantly gridlock. The system would crash before the first frame of your game even rendered. To prevent this chaos, computers rely on a critical layer of software, acting as a shield between your applications and the physical silicon, the operating system. Think of the operating system like a commercial building manager. It runs in a privileged kernel mode, granting it authority over the building's essential infrastructure. It manages the electricity, handles the plumbing, and monitors security for the entire site. Your applications, the video games and web browsers, are like individual businesses renting office space. They run in a restricted user mode, relying on the manager to provide them with the resources they need to function. The building manager's most high-stakes responsibility is acting as a microscopic traffic cop. It uses complex algorithms to funnel thousands of competing requests into the single-lane bottleneck of the CPU. The earliest strategy was first come, first served. Like a checkout line, the first task gets the processor until it's finished. But this creates the convoy effect. A slow-moving process takes enormous time to execute, creating a massive backlog of quick tasks stuck behind it. To fix this bottleneck, engineers developed shortest job first. In this model, the operating system actively reorders the line. It looks at all the pending tasks and bumps the ones requiring the least amount of CPU time to the very front. This clears out the quick tasks efficiently, but it creates a new failure state: starvation. If a system is flooded with tiny tasks, heavy jobs get pushed to the back of the line again and again, trapped in the queue indefinitely. The underlying problem is that basic chronological or size-based logic breaks down at computing speeds. Optimizing efficiency for the majority of quick tasks inevitably causes the operating system to neglect the minority of large ones. The next evolution was priority scheduling. This allowed the OS to identify critical tasks, like the data from your mouse movements, and give them VIP passes to jump to the head of the queue. To prevent low-priority background tasks from being ignored forever, the OS uses a technique called aging. The longer a task sits in the queue, the more the OS increases its priority level, eventually guaranteeing it a turn. Ultimately, prioritizing tasks still wasn't enough for true multitasking. The real breakthrough required abandoning the idea of waiting for a task to finish at all. This is round-robin scheduling. Round-robin treats the schedule like a spinning wheel. The OS grants every task a microscopic time slice, or quantum. When that expires, it aggressively pauses the task, saves its state, and banishes it to the back of the line while the next task enters. By enforcing these strict time limits rather than waiting for completion, the operating system guarantees true systemic fairness for all. It prevents any single application from holding the hardware hostage. This brings us back to that initial scenario: gaming, downloading, and streaming. Your computer is not actually doing those things at once. It is rapidly cycling between them using these scheduling rules and multi-level queues. Because the OS cycles through these slices millions of times per second, the gaps between executions are invisible. To your brain, the performance is seamless. This algorithmic evolution is what allowed computing to transition from singular batch jobs to the multitasking personal experiences we have today. Without the operating system acting as a light-speed traffic cop, the raw sequential power of a CPU would be entirely unusable for modern needs. This management of time transforms a rigid physical processor into a functional multitasking tool.